Okay, let's discuss the standard normal distribution. And 8.3 and 8.4 are both going to be discussed in this recording as they both are referencing the standard normal. We'll first start with the z-score, which is called a standard score, and then we'll discuss when we have our normal data sets, which are x variables with units. So the standard normal distribution is a normal distribution, typically bell-shaped, with a mean of 0 and a standard deviation of 1. That is standard. And standard meaning it never changes. You always have a mean of 0 and a standard deviation of 1. As a picture, we would see the mean is drawn in the center, as we learned from the empirical rule, that the mean is drawn in the center, and then we add and subtract the standard deviation on either side in order to form the normal curve. Now, some properties about this curve. The mean is always in the center. It's always 0. The standard deviation is always 1. So we'll always see the count of 1, 2, 3, -1, -2, -3. Now, where the first standard deviation is drawn, there is a point on the curve called an inflection point. It's about halfway down the side. And in calculus, which most of us do not have calculus backgrounds, and that's fine, but in calculus, this means the change in concavity. An inflection point means that the concavity is changing. And in layman's term, what that means is here's our frown. And when our frown starts to turn upside down into a smile, well, right between the frown and the smile, where you would split them off and say, okay, now it's starting to smile, is called an inflection point. And that inflection point is where the first standard deviation should be drawn. Now, remember from that empirical rule, that first standard deviation from -1 to 1 holds 68% of the area under the curve. Okay, so it is important where it's drawn. And then you just kind of estimate where 2 and 3 are. They're not necessarily identifiable points or easily identifiable points. And after 3 standard deviations on either side, we're talking about the outlier range. Between 2 standard deviations on either side, that is the usual range. And between 2 and 3 is fairly unusual, but not so unusual that we would consider it an outlier. The technique used to translate any normal variable x into a standard normal variable z is called a z transformation, or standardizing the random variable. So we know that when we are working in data sets that the data values have units, inches, pounds, miles. And when we want to compare is how far I ran or the time it took me to get from home to the store, which one was more unusual. We can't compare those directly when you have time in, let's say, minutes and distance in miles. It just doesn't compute. Even if we were working with the same units and we were talking about a house worth $300,000 in Winstead versus a house worth $300,000 in Avon, Connecticut, we're talking about Connecticut, you are not talking about the same kind of house. In Avon, you'd be getting, maybe a nice raised ranch. And in Winstead, you might be getting a beautiful, large, very large colonial. So because they're coming from 2 separate populations, 2 dynamics, 2 economic statuses, we cannot compare. Even though it is house to house, we can't compare them directly. And that's where this standard normal curve comes in. We are going to be able to take x variables with units and translate them into standard scores without units, allowing us to directly compare data values that are not from the same population and sometimes not the same in context. They don't have the same unit. Because the z transformation gives the standard normal unique status among normals, the standard normal is also referred to as a z distribution. Okay, so a z distribution or a standard normal curve, we're talking about the same thing. Now, first example, let's compute the probability that the standard normal variable is less than 1.27. And since we have a bunch of computational examples, I decided to do a side-by-side instead of switching back and forth. So in our Rguroo, we would go to our probability calculator, go to probability, and our probability calculator, but this time we are talking about continuous data. Okay, time, distance, weight. We are not talking about discrete variables anymore. So here is our continuous probability calculator, and we will go back and forth between calculating probabilities knowing values and finding values knowing probabilities today. We are using the normal curve. There are many continuous distributions, most of which we cover in the advanced stats class. But this class, we will be discussing the standard normal and the student t-distribution, but we will not be doing the t-distribution today. Now, when we're talking about standard scores, the mean is always 0, the standard deviation is always 1, which is why it's defaulted to those values. Now, less than, okay, so below, we have options of below, above, between, and outside. Now, we do not have the little checkbox that allows us to do less than or equal to, or the little checkbox that allows us to do greater than or equal to in this calculator. And that's because for continuous data, less than or equal to is the same probability as less than, because the next value below a certain value is infinitely close to the one that you're looking at. There are infinitely many decimals between 1 and 2, between any whole numbers. And therefore, when we go one less than 1, we're talking about 0.999999999999999. Okay, so within 4 decimal places that we're taking probability, it is absolutely the same probability. So for this one, we're trying to be less than 1.27. So we type in below 1.27 and we hit our eyeball and we get the probability of 0.89. And if we round, it's 0.8980 or 89.8% chance. Now, it doesn't really make sense to translate these into percentages because they're not word problems, so we don't have necessarily what we're talking about is the chance of. So let's just stick with areas. So 89% of the area is to the left of a z-score of 1.27. Now let's compute an area between two z-scores. So 0, a z-score of 0 is the mean, so that's directly in the middle. So if we're talking about an area of less than 0, it's exactly 50%, or greater than 0 is exactly 50%. This curve is symmetric. So we do and we can be confident that the mean of 0 is marking the 50% or 50 percentile, because remember, percentiles are areas to the left. So let's calculate between 0 and 1.27. So I'm going to come over here to my calculator. I'm going to select between, and the lower is 0 and the upper is 1.27, and eyeball. There is an area of 0.39796, which would round to 0.398. Okay, so about 40% of the area is between 0 and 1.27 on this standard normal curve. Let's determine now the probability greater than 1.37. So now I'm going to switch this to above, and I'm going to type in 1.37, eyeball. 0.0853. So approximately 8.5% of the area is above a z-score of 1.37. So one thing you'll start noticing is the farther we get out here in the tail, the area drastically reduces. But remember, the area under the curve represents the probability that an event will occur. And as we get closer to the outlier range, we should expect the probability to be ridiculously small. As we know, outliers are unusual, very, very unusual. So we wouldn't expect the probability of them occurring to be very likely. Let's try these 4 examples. So let's try the area to the left of Z is. Now notice that these examples are a little different. They are providing us with the area and the direction of the area, allowing us to, or asking us to find the Z-score when given a probability on a specific side. So if we come back over here to our probability calculator, we are now going to say, hey, we know the probability. We are looking for values. We're going to switch that up. We're still talking about standard scores, so the mean is still 0 and the standard deviation is still 1. Now our options are lower tail, which is when we say we're to the left, upper tail, which is to the right, between area, and we rarely ever work with outside tails. Okay, so right now we're looking at the lower tail because it's left, and we're going to put our probability in here of 0.9147. The z-score is 1.37. So there is an area of 0.91 or 91% of the curve is to the left of the area of 1.37 as a z-score, which makes sense because we said it was about 8.5 to the right in a previous problem. Okay, if we try the area between 0 and a particular z-score, we're saying that what z-score would give us an area of 36.65% between 0 and what? Okay, head back to your probability calculator. Select the between tails option. The lower they gave us was 0. Let's see, probability to value. So between tail, why do we have a lower? Let's hit the question mark. So let's figure this out together. So we have a question mark here, which defines each of these things, tells you when you're going from values to probability what they mean, and from probability to values what they mean. So here, the area between the return values is shaded, and the total probability is given. Okay. Well, I'm not sure that that's going to work well for us because we are looking to enter an area and find a z-score. So I don't see how this is. Let me see if outside works better now. Okay, let's do this differently then. If we are trying to find a specific z where we know that between 0 and z, we have 0.3665. Well, then what we can do is do a lower tail, because I just showed you on the graph that we know to the left of 0 is 50%. So if we add 0.5 to this area that is to the right of 0, we get 0.8665. And that will give us the z-score that marks the right side of this between area. So 0.8665. There's probably another way to do this, but I currently don't see how that works with our Rguroo, so this is what we'll do. So we have a z-score of 1.11. Great. That was one way to find it. Now, if this value wasn't 0, and let's say it was negative 1.85. So let's change this up real quick to negative 1.85 in z. Well, then for right now, what we would have to do is we would have to find the probability first to the left of negative 1.85. Okay, 0.032, and we'll round to 2, 0.0322. And we will have to add that to the area that they're saying is to the right of negative 1.85. So if we take in our calculators 0.0322 and add it to the 0.3665, that gives us a total left area of 0.3987. So now I'm going to go back to knowing the probability. I'll use a left tail. I'll put the total area to the left of the unknown z-score in order to get the z-score of negative 0.2567, which is to the left of the 0. Let's find an area to the left of a z-score. To the left, find the z. The area is 0.1469. So I am going to, again, this is a left tail, so 0.1469. And the z-score is negative 1.05 if we round. Z-scores are rounded to 2 decimal places. Areas, probabilities, to 4 decimal places. And let's do a right area. The right area is 0.7967. We're looking for that z-score. So I'm going to say this is the upper tail area, 0.7967, and the z-score is a negative 0.83 if I'm rounding to 2 decimal places. Now I put pictures in here as well, demonstrating area to the left, area in between. But again, what we did was we found that this was 50%. We did an area to the left to find the z, area to the left to find the z, area to the right to find that z that we just found, which is negative 0.8, which is right before the -1 standard deviation marker. In 8.4, we're going to discuss how to translate the x's and find probabilities. Now, we don't really have to do a hell of a lot of work when it comes to applications because this calculator will do it for us. The only thing we'll need to remember to change is the mean and the standard deviation parts. So the following formula can be used to transform any x value with units into a standard score if we needed to. We would use the formula z is equal to the data value in question minus the mean from the population that data value comes from and divided by the population standard deviation that this data value comes from. Let's find the probability. Okay, so it says find the probability. So I come over here and I make sure that what I'm finding is the probability that a normal random variable with a mean of 10 and a standard deviation of 20 will lie between 10 and 40. Now these are all x values. They don't really have units because this isn't a word problem that is particularly talking about a real situation. But the mean being 10, standard deviation being 20. We are talking about a normal random variable, so we are still in the normal curve. And we are trying to find a between area between an x value of 10 and an x value of 40. And the probability comes out to be 0.4332 when I round to 4 decimal places. Let's try some examples where we're actually talking about real life situations so that we can practice what we would say in conclusion after solving one of these. So suppose that a national testing service gives a test in which the results are normally distributed. That tells us we're using the standard normal curve with a mean of 400. Okay, so I'm going to type in my mean of 400 and a standard deviation of 100. If you score 644 on the test, what fraction of students taking the test exceeded your score? Okay, fraction, probability, decimal, same thing. So we want to know what is the proportion of students that taking the test exceeded your score. So we want to find the area to the right of a test score of 644 because that would be students who have exceeded your score. If you think of the number line, the larger numbers or better grades are on the right side of the number line. So that's how I knew it was a right-tailed test. So I'm going to do above a score of 644. And I can see that it is very low. 0.73%. Okay, that is less than 1% of students did better than me or the student on the test. Suppose that for 132 shoppers making a purchase at a clothing store, the total each shopper will spend follows a normal distribution. Good to know. We need to know that. With a mean of $234, so I'm changing that in Rguroo to a 234 mean, with a standard deviation of 94. What is the probability that the next purchase total will be between 100 and 150? So we're going to select between in Rguroo. We're going to type in the lower limit of 100 and the upper limit of 150 and calculate the probability. And we come out to 0.1088 when we round, which is a 10.88% chance that the next purchase total will be between $100 and $150. Lastly, let's talk about body temperatures of adults are normally distributed. Really important keywords. We are going to learn in future sections that when it doesn't state normally distributed, we have a little extra work to do. So we know that it's normal and it has a mean of 98.6 degrees. So I'm going to type that into my Rguroo with a standard deviation of 0.73. So less than 1 degree for the standard deviation. We want to know what temperatures represent the 90th percentile. Okay, this is a great review of percentiles. So we have to recall that a percentile is talking about the percent below a data value. So as you can see in this picture, notice that the mean is drawn at the center of the curve because we know it's normally distributed. A percentile means that 90% of the area is in the left tail, and we are looking for the data value that marks that 90th percentile. What body temperature marks 90% of people are below that temperature, and complementary, 10% of people have a higher body temperature than this X value we want to find. So because we're trying to find an X value and we already know the area under the curve, we need to select probability to values. And we know that the lower tail is 90%. So the body temperature that marks the 90th percentile is 99.54 degrees Fahrenheit. This concludes our lesson on the standard normal curve with z-scores, finding probabilities, and finding data values knowing the probabilities.